Chapter 11, Segment 2, we've been talking about London dispersion forces, dipole-dipole interactions, hydrogen bonds, and now we're going to tackle ion dipole interactions. So ion dipole interactions, so now what we're going to do is we're going to have an ion, and of course we'll put it in a polar solvent like water. And so now we're going to have our dipole coming from the polar molecule interacting with the ion of the opposite charge. Right, so we'll have our partial negative, in this case, of our oxygen attracted to our metal ion, or we'll have the positive end of our water being attracted to the negative ion. So attractions can be quite strong as ions, remember, have a full charge. So negative ends of water dipole surround the cation, positive ends of water dipole surrounds the anion. So here's the ion dipole attraction between aluminum chloride and 6 waters. So here you can see the aluminum is attracted to the 6 oxygens as it wraps around the aluminum ion. So the positive charge of the Al3 plus ion attracts the partial negative of the negative minuses for the water. The ion dipole attractions hold the water molecules to the metal ion, and we consider that a hydrate. All right, we can also have an ion-induced dipole attraction. So attractions between an ion and a dipole it induces on neighboring molecules. Okay, now this is going to depend on the ion charge and how polarizable the neighbors are. Attractions can be quite strong as ion charge is constant, unlike instantaneous dipoles of ordinary London forces. So we've seen this before where the dispersion forces across the molecule, remember, can go back and forth and sort of create a dipole, right? Here, that going back and forth was creating the dipole. Here it's going to be an ion, so we're saying it's going to be a constant. So for a dipole to occur between neutral molecules with permanent dipoles, right? So it's about 1 to 4% of the covalent bond, mid-range. Then we saw hydrogen bonding, special type of dipole. That was about 10%. For the dispersion, it was present in all substances. Okay, it's the weakest. The ion dipole occurs between an ion and a dipole. This is the strongest of all of the attractions. And now we just talked a little bit about an ion-induced dipole when it's induced by the ion rather than a second non-ionic compound. All right, so often we can predict physical properties like boiling point, melting point, and many others by comparing strengths of the intermolecular attractions from strongest to weakest here. So we have ion dipole, then hydrogen bonding, then dipole-dipole, then London forces. All right, so if you're looking at a comparison table between compounds and we're looking at boiling points, then really what you're trying to explain is it an ion dipole? Is it hydrogen bonding? Is it a dipole-dipole? Or is it just straight up London forces? All right. So physical properties depend on how tightly the molecules pack. For instance, compressibility. We can measure the ability of a substance to be forced into a smaller volume. Okay, so that's going to be, again, dependent upon the intermolecular forces. The stronger those forces, then the easier or harder, right? So the harder it would be to compress. So gases, for instance, are highly compressible because the molecules are starting far apart. That means they have very weak intermolecular forces, and as they compress to a liquid, those intermolecular forces become a little stronger until we finally get to solids, where we're almost nearly incompressible. Okay, so molecules here are going to be very close together, and obviously they have stronger molecular forces. Now we've looked at diffusion before. So diffusion is the movement that spreads one gas through another gas to occupy space uniformity. Okay, so spontaneous intermingling of molecules of the two gases. So again, remember the gas particles are moving, and what diffusion is looking at is if I have gas A and gas B, how quickly are they becoming a combination of the same container with both gases. All right, so this is going to happen obviously more rapid in gases than in liquids. It doesn't really happen at all in solids. And that should make sense. If I take two solids and I put them next to each other, they don't diffuse and become one in most cases. But if I take two liquids and I put the two liquids together, then you can slowly see one diffuse into the other. And if we're looking at gases, we're saying that's going to happen a lot faster. So in gases, remember the molecules are traveling larger distances and at higher speeds. And with liquids, the molecules are already close together. They encounter more collisions, but they also bounce around, which takes a longer time to move from place to place. And in solids, it's close to zero at room temperature because, again, they're pretty much steady in spot. They're not moving around at all, just vibrating. All right, so retention of volume and shape. Solids retain both their volume and their shape, right? That's because they have the strongest intermolecular attractions. Here's where our molecules are typically the closest. Now, obviously, you can think of some exceptions like water, where we see an expansion. We've talked a little bit about that already. Liquids retain their volume, but not their shape, so we consider their attractions to be intermediate. And then gases, of course, will expand to fill their containers, so they have the weakest of all of the attractions. Oops, all right, so how does temperature affect it? Well, they decrease with increasing temperature. And that kind of makes sense, right? As we speed the particles up, they start to move towards a gaseous state. Then we're going to see that everything weaken. The next topic we look at is surface tension. Why does water beat up on a freshly waxed car instead of forming a layer? So inside the body of a liquid, we have intermolecular forces are the same in all directions, right? So if you think about a water molecule and how it interacts with all the water molecules around it, all those forces are going to balance out. Now, molecules at the surface, though, potential energy increases when removing neighbors. So, trying to move these guys in and out, we're going to see some energy change. Molecules move together to reduce the surface area and potential energy. So, cause a liquid to take the shape, which is a sphere that minimizes its surface area. So molecules at the surface then have a higher potential energy than those in bulk of liquid and move to reduce the potential energy. So in other words, wax is nonpolar, water is polar. That's going to generate a dislike, a hydrophobic interaction. The water then will beat up in order to reduce the potential energy by reducing its own surface area. Liquids containing molecules with strong intermolecular forces will have a high surface tension, right? So we know water has a lot of intermolecular force, plenty of hydrogen bonding, which is about 10% of a covalent bond. And so since it has a high level of bonding, it's going to then tighten up to make a tighter sphere, which is going to give us a higher surface tension. So it allows us to fill the glass above the rim. So you've actually seen that where the water will bead over the top, kind of making a pseudo circle, if you will. Gives the surface a rounded appearance at the top, and of course it acts like a skin that lets the water pile up. Okay. So surface tension increases as intermolecular forces increase, and of course surface tension will decrease as temperature increases. So if we heat that water up, then the surface tension will decrease and it's more likely to just spill over. All right, there's the term wetting. This is the ability of a liquid to spread across a surface to form a thin film. Right? Water, of course, does that. So a greater similarity in attractive forces between liquid and surface yields water a greater wetting effect. All right, kind of going through this a little fast. Not going to worry too much about this. I think you can kind of read these. Because of wetting, we can lead to surfactants, right? Added to detergents to lower the surface tension of the water. So now water can spread out on a greasy glass. Okay, so we're looking at a soap molecule here. Substances that have both polar and nonpolar characteristics. So you can see we have the salt, if you will, end, that polar charged end. And then we have this long carbon chain. So each one of these little dots is a carbon. And so we have a long carbon chain, which of course we know has no polarity to it. So it's a nonpolar tail with a polar head, if you will. Long chains of hydrocarbons with a polar tail. Well, here they're thinking of it as head this way, tail that way. Nonpolar end dissolves in the nonpolar grease. And of course, the polar end will dissolve in water, thus increasing the solubility of grease in water. So now the soap can wash the grease away using water. Now, viscosity is our next topic. It's the resistance to flow. So if you've ever seen the commercials with Castrol GTX, and they're talking about viscosity and thermonuclear breakdown. So what they mean by that is the engine gets hot, the metal starts to expand, and boom, the engine will lock up. So what we'll do is we'll put oil in there, keep everything lubricated down, and keep the engine kind of cool. We also will flow water through valves within the engine to keep the block cool. Viscosity is a measure of a fluid's resistance to flow or changing form. So its form, as it changes form between physical states, its viscosity will also change. The viscosity is proportional to the intermolecular attractive forces. Okay, so it's going to depend on how molecules in a substance interact with each other. The viscosity will decrease when the temperature increases. Most people associate liquids with viscosity. For instance, syrup is more viscous than water. Now, gases also have viscosity, and they respond almost instantly to form-changing forces. Solids, such as rocks and glass, also have viscosity. They normally respond very slow to forces acting to change their shape. So what is the effect of intermolecular forces on viscosity then? Well, if we take something like acetone, it's a polar molecule, and it has dipole-dipole interactions as well as London forces. Then we'll take a molecule like ethylene glycol, also a polar molecule, has some hydrogen bonding, and dipole-dipole and London forces. Which one of these would we expect to be more viscous? Now, I'll give you some formulas. Whoops. Didn't give us the answer there. So which one would we expect to be more viscous? Well, obviously the more interactions we have that are stronger, the more solid-like we'll become. The more solid-like we become, the higher we expect the viscosity to be, so the more viscous. Okay, so acetone flows like water, ethylene glycol would flow like syrup. All right, now they're giving us pairs. So for each given pair, which is more viscous? C6H14 as a straight chain. Oh no, so they're saying we still have a straight chain. 1, 2, 3, 4. So we have a butanol. So we have an alcohol in the end. And then, so we didn't really talk about these functional groups. So that's going to be an OH. And then here we have CHO is going to be a C double bond O with an H. Okay, so that's going to be an aldehyde. So alcohol or aldehyde, which one we expect to be more viscous? Then the straight chain carbon with 6 or with 12. And then ammonia as a liquid versus the pH3 as a liquid. All right, so let's see, we'd expect the alcohol to be more viscous than the aldehyde. Right, this hydrogen isn't really ionizable, this one is. So that's going to give us our polar bond. So aldehydes have a little bit of polarity, but alcohols have a lot. So it's got hydrogen bonding going on. This is very minimal hydrogen bonding. So that's going to limit us to A or B. And then would we expect the C6 or the H12? And of course, the larger these molecules are, the more solid-like they become due to London dispersion forces. So we're going to probably expect C12H26, which means our answer would be B. And it looks like our only options there would be ammonia as well. And of course, there we go. There's the reasoning behind it. All right, so solubility, like dissolves like. So to dissolve a polar substance, we'll use a polar solvent. And if you've ever played with super glue, then you might know that if you super glue your fingers together, water will not help you get them apart, right? And that's because super glue is methacrylate. It is a very non-polar substance. Water, of course, is a polar solvent. The polar solvent cannot dissolve the non-polar material. However, if you get some gasoline and you rub that on your fingers will come right apart. And that's because the non-polar gasoline will dissolve the non-polar superglue. So to dissolve a nonpolar substance, we'll use a nonpolar solvent. To dissolve a polar substance, we would use a polar solvent. Now, compare relative polarities. Similar polarity means greater ability to dissolve in each other. So if you have two materials that are very polar, they will dissolve much easily and diffuse much more quickly than a very polar with a slightly polar, right? And as that polarity, so if I start with a very polar material and start to go with a non-polar, change, then you would slowly see that you're going to end up with a non-dissolvable material. So differing polarity means that they don't dissolve and they become insoluble. That's part of the way surfactants were working. They both have polar and nonpolar characteristics. This separates the water from the material, right? Or in the case of surfactant, allows the material to blend. So like putting a surfactant in soap helps the soap and the water mix together to get through the fabric. All right. Which of the following are not expected to be soluble in water? So HF, CH4, CH3OH, or do we expect them all? And hopefully you said methane CH4 is not going to be soluble in water. What type of intermolecular attraction causes Ki to dissolve in water? Hydrogen bonding, dipole-dipole, dispersion, ion dipole, or none of the above? And hopefully you've picked ion dipole. All right, next up is phase changes, changes of physical state. So we'll deal with the motion of molecules. We've kind of looked at this already from a couple different perspectives, maybe not directly. So here we're going to speak to that. As your temperature changes, matter, of course, will undergo a phase change. So as we heat it up, we will see that a solid will turn to a liquid. We call that a melting point. Then, of course, from a liquid to a gas, call that an evaporation point. All right, so evaporation or vaporization. Now, as heat is added, water forms steam or water vapor. Right, it's going to require energy or a source of heat. So when we look at phase changes, solid to gas, a sublimation, ice cubes in the freezer, if you leave them in long enough, they will disappear. This is an endothermic reaction. Okay, now gas to liquid, condensation. Dew is H2O vapor condensing onto the cooler ground, often limits the lower nighttime temperature. Let's see, rate of evaporation, not too worried about that. I'm going to go through that kind of fast. You can read that on your own. The effective temperature on the evaporation rate. So for a given liquid, the rate of evaporation per unit surface area increases as temperature increases. So why is that? Of course, at a higher temperature, the total fraction of molecules with a kinetic energy is large enough to escape, and so that's going to be larger. All right. So changes of state involve equilibrium. We haven't really talked about this, so we'll slow this down here. So when we take a solid and we transform to a liquid, more often when we go from a liquid to a gas, what we're going to do is set up an equilibrium. So there's a fraction of molecules in the condensed state is higher when the intermolecular attractions are higher. Now, intermolecular attractions must be overcome to separate the particles, while separated particles are simultaneously going to be attracted to one another. So in other words, what we're saying is if I take a container and I seal it off and I've got some liquid in here and I've got some of its gas in here, there's going to be some of these molecules going into the gaseous state as they get enough energy to get out. And of course, the ones that are in the gaseous state are eventually going to run into each other, become attracted, and become a liquid. And so we have a dynamic equilibrium going on between the two phases within the container. So if a liquid is placed in an empty closed container, it begins to evaporate. Now, once in the gas phase, the molecules will begin to condense from striking the surface or the liquid and giving up some of their kinetic energy. So once the system's at equilibrium, the rate of evaporation will equal the rate of condensation. Now, this occurs in a closed system where molecules cannot escape. So remember, closed systems versus open systems, right? This dynamic equilibrium will take place inside our closed systems. Now, similar equilibria can be reached in melting, except now we have a solid going to a liquid, and then the liquid freezing and coming back to a solid. So the melting point, the solid begins to change into a liquid as heat is added. The dynamic equilibria then will exist between the solid and the liquid state. So the melting, the red arrows, and the freezing, the black arrows, are going to occur at the same rate. Now, as long as no heat is added or removed from this equilibrium mixture. So if we continue to add more and more heat, then of course we're going to pass that system of equilibrium and go directly to the liquid. We can play the same game with sublimation. So at equilibrium, the molecules sublime from solid at the same rate as molecules condense from the vapor. All right, so it's the same game. Now, one way to look at these is what we call a phase diagram. So we can look at phase changes here. So we have a liquid, and of course the liquid, we have a solid. The solid can turn into a liquid, which can turn into a gas. The gas can then condense back to a liquid, freeze back to a solid. The solid, of course, could skip the liquid phase, go right through sublimation, or the gas could hit deposition and come back to solid. All phase changes are possible under the right conditions. In fact, you can look up a video on what's called the triple point, and all of these things can happen at the exact same time. Now, following our sequence is going to be endothermic. So we go heat from a solid, it melts to a liquid, we heat it, it's going to boil, and we get a gas. Right? So in each case, we're giving it energy, and so that's going to be endothermic. It's receiving that energy and then changing phase. If we work it backwards, it's going to be exothermic. So we'll have our gas, right? We'll cool it down. It's going to condense. We're pulling energy out of it. That's exothermic. Cool the liquid and it freezes, and we make a cool solid. Now we can set up heating curves. You can run these on what's called a DSC machine, differential scanning calorimetry. So we'll put our substance in. We'll then start to add the heat, and what we'll see is if it were a solid, it's going to go up, and then all of a sudden we're going to get this boom. So that's just a phase change. We're going from solid to liquid. We get melting. Then it's going to start to receive heat again. And then we're going to see, boom, a little bit of superheating, but really what's happening is you have some superheating here too. We just don't see it usually in a blip. It just keeps going. And then boom. All right, now it's going to be all same temperature as it then approaches the gas. Okay, so horizontal lines are going to be your phase changes. It's a good way to find melting points and boiling points of different, in my experience, it was always plastic materials. Now we can also cool it down. So this was another experiment you could do on the DSC. So now you're going to start with your gas. You're going to let it cool down, and you'll see the curve just be the opposite. And then, of course, here we get some supercooling where it goes past and then starts to realign itself. So horizontal lines, that the phase changes again, melting point, boiling point. The diagonal lines, of course, are your cooling of the solid, liquid, or gas. All right. Now we can come back to enthalpy again. Actually, I think we'll take a break here in the middle of this. How many more slides? Yeah, we'll take the break here and break it up. And in segment 2 on enthalpy change. So before we bring enthalpy back into the picture and look at this from the heat point of view and H point of view, we'll take the break here after cooling curve. So stay tuned for segment 3. Should be a little bit different, I guess, bringing enthalpy back in and thinking of this in processes of heat.